Welcome to video 1 in our Spatial Econometrics series of videos. Again, I'm Mark Berkey, and you can find information and indexes of all these videos on Berkey Academy, which is a YouTube channel, or on www.berkeyacademy.com. And all of the handouts and other files that I'm going to be using here, I'm going to try to make as many of these things available as I can on my website, berkeyacademy.com. Let me just show you that real quickly here to help you find where I'm going to put these things. If you go to www.berkeyacademy.com, then if you go see this little link here on the left side, Files, if you click there, I try to put as many files with data sets and handouts and things as I can right here. And I think what I'll do for this Spatial Econometrics video series is I'll put the files here to download, but what I'll do is I'll begin the name of all of the files with SE, so they'll be a little bit easier to find in alphabetical order. So I'll probably name this file SE video 1, something like that. So you can download this and you can look at it and have it in front of you. So go ahead, download this, print it out so that you can look at these models, because what we're going to talk about here is important as an overview, but there is some technical information also with all of these equations. So it's good if you have it so that you can take notes. So what I want here to do is give you an overview. It's going to be an intuitive overview, believe it or not, even with all these equations, about what spatial econometrics is about and what we can do and why it's important. So the first thing I want to do before we talk about spatial econometrics is to give you the ability to map things, because if you can't visualize your data, all is lost. So we need to start by giving you a tool to map some things. And so a free GIS program, it's similar to ArcGIS, but it's much cheaper, is called Map Window. So go download that, and then I'm going to show you how to download some free map files. So just Google it, MAP window, Map Window, and just click here, Map Window, Open Source GIS, and you can download. This is the work in progress version 6. Just download version 4.x, whatever here, and install it. Now, I do my work on a Microsoft Windows-based machine, so you're going to have to figure things out your own a little bit if you use Linux or a Mac or something like that. I don't know much about those platforms. So download it and install it and run Map Window, and when you run it, you're going to open up something like this. Let me shrink this down so that you can see the whole thing here inside my video window here. So when you open it up, there's nothing there. What you need to do is to download some files so that you can add some layers. Let me show you the basic procedure here. The kind of files you want to try to find are SHP files. So let me go here. You want files that end in a .shp. Now, SHP is called a shape file, SHP. Now, when you have a shape file, it's not actually just one file. A shape file, what you need for it to work is a collection of files. Usually you'll have one file that ends in SHP. That needs to be in the same directory as another file that usually will end in SHX. There are a few of them that may or may not be present. SHX, another one might be .dbf. This will actually contain numerical data associated with the map file. But as long as you download a SHP file, it'll usually come packaged with these other files that are necessary. And so let's go ahead and download one. I want to look at the 48 states in the United States. And if you want to download a file, just go to Google here. There are plenty of places where you can download map files for free. You can pay for them too, but don't don't buy something that you can get for free. We could do like U.S. states SHP. That way you'll know that you're getting the shape file. And here's a link that says .shp and download compressed shapefile. That sounds like what we want. So this is the National Weather Service. There are a lot of places that have these files for free. Let's download this zip file here. So I'm going to save it. And once it's saved, let me open the folder here. We have a zip file. What we want to do is extract this folder so that we can use it and add it to a map. So I'm going to use the program 7-zip. That is another free program. And what that just did is it extracted it to a folder down here with all of those files in it. Now I'm going to drag that off to my desktop so that I can easily add it. So what we have here, let me just open up this file just to show you what you're going to see. So there's no mysteries involved here. This is actually a folder that has the DBF file, a PRJ, that's a projection file, because the Earth is round, and in order to view it as a flat surface, we need to tell the program how to take the round globe and make it flat. That's a projection. Here's the shape file, here's the SHX file. So usually you'll have 3 or 4 files like this. And what we want to do now is go to our map window program and click Add. Not Open. It's misleading, I know, but click Add, and that will let you add a layer, which is a shape file or some other file. So when you go to that little folder we just downloaded for free, this is the shape file we click on, and let's see. Now nothing happened. This is odd, but what's happening here is it wants us to click this little box here for some reason, which shows or displays or doesn't display that layer file. So it can be frustrating working with these maps. And I'll try to make it as easy and straightforward as possible. So here we have Alaska over here. What we want is the pan button here. So we can look at maybe Hawaii. Here's Hawaii out here in the Pacific. There's Alaska, and here are the other states. Now, why did I go through all this? Well, in order to talk about spatial econometrics, you need to be able to visualize some regions and ask yourself how these regions might be related. So as an example, let's look back at the little handout here. Let's think about, what if we wanted to run a regression? We wanted to model the unemployment rate. So suppose that's our y, our dependent variable is unemployment rate. And we wanted to use the 48 contiguous states plus Washington, D.C. Why would we do that? Well, we could include these other states, Alaska and Hawaii, but I'm sorry if you're from Alaska or Hawaii, but I'm going to leave them out for right now because they are not contiguous. What's contiguous mean? Well, contiguous means they touch each other. So sometimes people will talk about the 48 contiguous U.S. states. That means the 48 states here that touch each other. And Washington, D.C. also is contiguous. It touches, so sometimes we'll include that as a 49th region. It's not really a state, but it's a region. So suppose we wanted to study unemployment. We could create a model. Unemployment is a function of some explanatory variables x and some slopes b. Now this is just a different way, a more compact way of writing this kind of model. That yi, unemployment rate in a state, is equal to a y-intercept plus a slope times explanatory variable, and we might have many of these explanatory variables, plus some residuals. This is the same thing written in a more compact notation. We might have 10 explanatory variables, x's, and 10 slopes, plus a y-intercept, all written in this compact notation. Here we'd have to write them all out separately. B2 plus X2I, blah, 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 etc. So we're going to write it this way in the more compact matrix and vector notation. So we might have explanatory variables that explain the unemployment rate, such as income or investment or number of businesses, education, etc. We might have a lot of these explanatory variables that help explain the unemployment rate in a state. But then there's going to be a residual, something we can't explain. So we have unemployment rate, explanatory variables, income and education maybe, and residuals. Now, if we run an OLS model, that might or might not do a good job of explaining the unemployment rate. Why might it not do a good job? Well, here's where the idea of spatial econometrics comes in. Let's go look at our map again. Let's suppose we were looking at the southern region of the United States, just to focus on it. I'm from North Carolina, which is right here. Here's South Carolina, this little thing right here. Regions might be related to each other in a way that's not measured by our model. How might that work? Well, there are three ways that we think about that. Say the unemployment rate in North Carolina might be related to the unemployment rate in South Carolina and Virginia and Tennessee and Georgia, its neighbors. How might that unemployment rate be related among these states? Well, there are three ways. Let's go back to our handout here. Regions might be correlated with their neighbors in three different ways. Before we talk about that, let's talk about neighbors. We're going to measure neighbors by something we call W, which is called a spatial weights matrix. And W is just a way of telling us who our neighbors are versus who our neighbors are not. And there are a lot of ways to measure neighbors. We'll get into the details later on. Let's just assume now we're talking about neighbors in a very common sense way. The neighbors of North Carolina are states that it touches. There are other ways to do this, but let's just suppose that's Virginia, Tennessee, Georgia, because they touch right here on this little edge over here, and South Carolina, it touches. So those are our neighbors. How might our unemployment rate in North Carolina be related to what's going on in neighboring states? Three ways. First, the value of Y, the unemployment rate itself, might impact or be related to the value of Y in neighboring regions. So the unemployment rate in Virginia, South Carolina, Tennessee, and Georgia might somehow be related to or cause, but it doesn't have to directly cause, it just might be related to in some other way, the unemployment rate in other states. So for example, there might be some variable that we're missing, some variable that we're not observing, that we don't have as an explanatory variable here, that is nevertheless spatially related. Or it could really be a causation effect. It could be that because there are a lot of unemployed people in Virginia looking for jobs, that some of those people looking for jobs come looking for jobs in North Carolina. Maybe they move to North Carolina looking for jobs. Well, that's going to increase the unemployment rate in North Carolina if the unemployed people spill over, for example. That's just one of many ways this could happen. So you could have high unemployment rate in a state causing or spilling over to another region. That's one possible explanation. It could also be that the values of X in one region might affect the unemployment rate in the neighboring region. So the X's, the education and income in Virginia, South Carolina, and Georgia might affect Y, the unemployment rate in North Carolina. Well, how might that work? Let's look at our map again. Well, it might be that in Virginia, people have high incomes, And those people with high incomes buy a lot of products. Where are those products going to come from? Well, some of those products that people in Virginia buy might be coming from North Carolina. They trade with each other a lot because they're located next to each other. People from Virginia might drive to North Carolina to shop at stores, or they might just buy, vegetables, fruits, clothing made in North Carolina and Virginia. So the fact that people have a high income in Virginia, might lower the unemployment rate, the Y, in North Carolina. So that's a second way that things might be related. So it could be that the Y's in Virginia, the unemployment rate affects North Carolina's unemployment rate. It could be that the X, the education and income in Virginia, might affect the unemployment in North Carolina. Or third, the residuals in Virginia might affect the residuals, the E's, in North Carolina. And this is an idea of spatial heteroscedasticity, is the way I like to think about it. So it might be that the E, if we observe a high unexplained value of unemployment in Virginia, that might somehow help explain why it is that there's a high unexplained unemployment rate in North Carolina. So it could be that those residuals are spatially correlated, and if so, that means that these residuals are not just purely random white noise error terms. There's something predictable in those error terms, and that causes spatial heteroscedasticity. If heteroscedasticity means that the error terms aren't all coming from the same distribution, just a random white noise distribution, so they might be spatially related. So that's what we call a spatial error relationship. So here we have a spatial relationship in the dependent variable, the y's. B, we have a spatial relationship between the x's in the neighboring regions affecting our y. Or it could be that the spatial residuals are affecting our residuals. Three different ways of looking at it. Now, how do we write these models down in formal terms? Well, the most general kind of model is called a Manski model, a spatial Manski model. Now, the Manski model says, just translating this into English, that y, the unemployment rate in North Carolina, say, can be explained with neighboring unemployment rates, WY. So W just says neighboring values of y. How much are they affected by neighboring values? Well, that's this rho character. Looks like a P, but it's the Greek letter rho. So rho would measure how much, if any, do neighboring values of unemployment, W, neighbor, unemployment, how do they affect our unemployment? Plus XB. This is nothing new. This is just our own values of unemployment, our own values of income and education in North Carolina, plus our neighboring W values of education and income. And theta measures exactly how strong are those neighboring relationships, and are they positive or negative. So theta measures the degree of the relationship of our neighbor's x's, is all that's going on here, plus u, a residual. But in the Manski model, that residual is more complicated. It says that our residual, our unexplained value, the variation in unemployment we can't explain, is a function of lambda times our neighbor's unexplained variation in unemployment plus some white noise term. So this is the Manski model. The Manski model builds in all three of these types of spatial relationship that you can have. Now, the problem with the Manski model is that it's very difficult, if not impossible right now, to get good estimates of this full kind of model. So it's a model that now I'm not a 100 I'm not one of the top experts in the world of this. I'm sharing with you the basic ideas. We'll get into the more details of this later on. But basically right now people are reluctant or do not estimate the Manski model because you can't get good estimates for how the neighbor's y's affect our y, and at the same time how their x's are affecting our y, and how their residuals are affecting our residuals all at the same time. So normally what we do is we estimate one of these less involved, less complicated models. So what if we drop out one of the three? So what if we don't have all three of these things in the same model? What else can we do? Well, if we drop this part, the lagged x's, we drop the lagged x's, theta equals 0, the Manski model becomes what we call the Collegium Purusha model. Or Collegium Purusha model. This is by Harry Collegian and Ingmar Purusha at the University of Maryland. Just dropping out this term, we have this model that basically says we have the lagged y values and the lagged error terms. That's the Collegium Purusha model. And those guys think this is the best model to estimate, at least to start with. However, there's a different camp of people who think that the best way to start is to estimate the spatial Durbin model. This is basically Lesage and Pace. Their standpoint is you should start with the spatial Durbin model. The spatial Durbin model has the lagged y's and the lagged x's in the model, but drops the spatial error terms here. So that's what we call the spatial Durbin model. Let lambda equal 0, you're dropping the lagged error terms from the model. Now what if we take the spatial Durbin model and we simplify it? Well, there are three ways you can simplify the spatial Durbin model. And this is what's really cool about the spatial Durbin model. There aren't just two ways to simplify it, there are three. Kind of misleading, kind of not straightforward to see, but I'll show you this. If we let rho equal 0, then this simplifies into only having the lagged x's, no lagged y's. So that's what we call the spatially lagged x model, or the SLX model here, where you have the spatial values of the x's times the theta. That's the SLX, or spatially lagged x model. If instead we take the spatial Durbin and we let the theta equal 0, so take the spatial Durbin, we can get rid of the spatially lagged x's if they're not needed, and then we just have the lagged y's. So if the thetas are all 0, and there's actually one theta for each explanatory variable, then that degenerates into the spatial lag model. Y is a function of the lagged values of y's, rho times the neighbor values of y's. That's called the spatial lag model, or some people call it a SAR model, the spatial autoregressive model. Spatial lag y, or spatial autoregressive model. So there's a third way, though. You can restrict the spatial Durbin to become the spatially lagged x, or to become the spatial lag y, or spatial autoregressive model, but then there's a third cool way that you can restrict it to become the spatial error model. If theta, the coefficient on the x's, is equal to minus rho times beta, then it becomes just a model where the spatial errors are correlated. Now, here's how to see that. Now, warning, the math below is probably not technically correct because I am not a matrix calculus or matrix algebra expert. But this is so you can basically see how this restriction gives you just this very simple model where the errors are spatially correlated. So what we do is we take that spatial Durbin model And if the theta here, set it equal to minus rho beta, then that's what we have in the next line here. Also, to simplify this, what is y? Well, y equals x beta plus epsilon, right? Plug that in there. And by doing some simplification here, distribute rho w times x beta and rho w times e. We have these two terms. We have the wx times minus rho beta. What's going to happen here? Well, wx times minus rho beta and this rho wx beta. I know these are in the wrong order. You don't have to write me emails and correct me. I already said that up here. So this is just so you can get an intuitive feel. This term and this term are going to cancel. Wx minus rho beta and positive rho x w beta will cancel. And so what are you left with? You're just left with x beta and rho we, basically, and the e. So you've got basically this model. And again, that's not a formal derivation, but that's to give you the intuition about how can you get from the spatial Durbin model and by restricting it, get the spatial error model. The reason that Lesage and Pace favor the spatial Durbin model is you can definitely estimate the spatial Durbin model, and through restrictions it's very easy to either get the spatial lagged X model or the spatial autoregressive model or the spatial error model. So you can test these restrictions to see which the right model you should estimate would be if you start by first doing the spatial Durbin model. And that's the approach I like best. I'm convinced that this is a very good, appealing way to start by doing the spatial Durbin model and then testing restrictions. Now, the other main camp of people, now there's also Collegium and Purusha. They, and I apologize if I'm mispronouncing Purusha here. There's that camp, the Collegium and Purusha camp, that say you should start with this model. But then there's a third camp that is the Anselin camp. Luke Anselin, and I took a class from Luke Anselin a few years ago when he was at the University of Illinois. Luke Anselin takes a different kind of approach. He says you should start with the OLS model and estimate that. And then, instead of starting with a spatial model and seeing if you can restrict it to OLS, he says start with OLS and then do some tests to see if you should add spatial terms. And so those are three different camps that say how you should specify a spatial model. Anselin, start with OLS and see if you should expand that to the spatial error or the spatial lag model. Collegium and Purusha, who say start with this model and see if you should restrict it. At least I think that's what their philosophy is. Or Lesage and Pace, which say start with the Durbin model, spatial Durbin, and then test to see if you should restrict it back to make it simpler to become the spatially lagged X, the spatial autoregressive, or the spatial error model. And that's what I like. But there are a few other ways that you can try to specify a model as well. And we're going to talk about all of those as we go through the various lectures here. So that's all the various models. I know that's throwing a lot at you here in one video, but until you see the forest, you can't appreciate the trees that are in the forest. So hopefully that will get you started to thinking about how these different models might work. And what we're going to start doing now is start getting into the details. How do you specify weights matrices? How do you estimate these models? And those are going to be a long series of videos to come. So I hope you join us. And if there are any questions about any of this, please feel free to write me. You can contact me through berkeyacademy.com, or you can comment on this video below. Thanks for your interest.